So in previous lecture we discussed about analog to digital converter and how to interface analog to digital converter with 8051 microcontroller, and we have seen one program also. Now to control the environment, we have to operate the actuator. To operate the actuator, we require analog signal. Basically, if we see the structure of a controller based system, then it will be like this. There will be one sensor, right? This sensor will convert, so this is here, this is the environment. So here we are having some physical quantity. So this physical quantity will be sensed by the sensor, and this sensor will generate here some analog signal. Right? Now this analog signal will be passed through one ADC, analog to digital converter, ADC. So this ADC will have now here digital signal. Now this digital signal we will feed to microcontroller or processor. So this signal is the input to processor. So processor will process over this digital signal and it will generate digital output. Sometimes these digital outputs are directly used in applications, but in some applications we again require analog signal. So we have to convert this digital signal, which is the output, again to analog. So here we are now requiring one DAC. So DAC will generate analog signal. And this analog signal will be used to run our actuator, right? Like motor. So here we have connected one motor. This is motor. So one simple application is, suppose we want to control the temperature of this room. So there we will use a temperature sensor IC like LM35. It will sense the current temperature of the room. Then it will generate the analog signal. Analog signal will be passed through analog to digital converter. Here we are having digital signal. So processor will process this digital value. It will generate some digital output. Again we will convert the digital output by using DAC, digital to analog converter, into analog signal. Now with this analog signal we will run the motor, or like fan, or the compressor of the air conditioner. So when this compressor or fan will run, then it will bring down the temperature of the room. So in this way, this is the whole structure of a system. So now here this DAC is also play an important role. So we will discuss about this digital to analog converter, and the particular IC which we will discuss is 808. So this 808 DAC is a 8-bit DAC. It is having 8-bit digital input lines. So suppose this is our DAC 0808. These are input lines of this DAC, and there are 8 input lines from D7 to D0. Now here the output is generated in the form of current in this DAC. So here we will get I out. This is the output current. So if we require a voltage to run some motor, then simply we will convert this current into voltage. For that, externally we will connect some resistor. So suppose this is load resistor, and we will take the output across this. So here we are having output, V out. So this output you can use to run some motor. Here we have connected the motor. This is plus end, minus end, and you can vary the speed of this motor if we are able to vary the amount of this output current. So output current value will now depends upon the digital input. So if we change the digital input, then the this I out value will also change, and if this value will change, then the output voltage will change, and if output voltage will change, then the speed of this motor will also change. So in this way we can control the speed of fan or compressor of the air condition, anything. Right. So and here we have one, this is an input pin. There is one resistor you have to connect. This is R reference plus resistor, and this end is connected to V reference plus. There is another input pin. Again we have connected one resistor. This resistor is named as R reference minus, and this end is connected to ground. So these are two input pins. Now in this DAC there are other pins also, but these are more important pins. We will focus over those pins. Now to generate this output, the formula how to calculate this output, the formula is this: I out is equal to I reference. There is some reference current which is internally generated inside this DAC with the help of this resistor and this voltage. Multiply by, now we are having 8 data lines. So D7 by 2 plus D6 by 2 plus this is 4 plus D5 by 8 plus D4 by 16 plus D3 by 32 plus D2 by 64 plus D1 by 128 plus D0 by 256. So this is a formula to calculate the output current. Now here this I reference for this DAC has to be maintained at 2 milliampere. So it has to be fixed at 2 milliampere. Now this reference current will be generated by using this reference voltage and this reference resistor. Now suppose we are operating this DAC at V reference plus of 5 volt. Then we have to select the value of this resistor. So now we can find out the value of this resistor. We know that this I reference will be V reference plus we have to calculate R reference plus by I reference. Now V reference plus we have fixed it at plus 5 volt, and I reference we have to keep it at 2 milliampere. This is 2 milliampere. So this will give you a value 2.5 into 10 raised to the power 3 ohm, or 2.5 kilo ohm. So in this way we will fix the value of R reference plus, so this will be 2.5 K. Whatever value we will select for R reference plus, same value we will use for R reference minus. Here also we will use 2.5 K or kilo ohm, divided by kilo ohm. If we change this V reference plus voltage, suppose we make it 2 volt, then the value of R reference will be, so here V reference plus will be 2 volt, and I reference we have to maintain at 2 milliampere. Always we have to maintain at 2 milliampere. So in that case the value of this resistor will be 2 kilo ohm. So same way you have to connect here also 2 kilo ohm. So in this formula, I reference is equal to 2 milliampere. Now depending upon the input digital value, now we will get some output. So that bit position which is equal to 1, we keep that 1 in this formula. And if the input position is 0, then we keep that bit position 0, and we will use this formula to find out the value of I out. Now I out is approximately equal to I reference. Maximum, I am talking about I out. Maximum is approximately equal to I reference. That it is very much close to 2 milliampere, but slightly less than I reference. So always I out maximum is less than I reference. So maximum output current what we will generate here, we can generate here, that will be slightly less than I reference. So what will be the maximum I out? So you will get the maximum I out if our digital inputs are, these are digital input pins D7, D6, D5, D4, D3, D2, D1, D0. Okay, if all of these input lines are at 1, then we will get maximum I out. So in this case, what is the value of I out? We will calculate this. I out is equal to I reference is 2 milliampere multiplied by, now we will replace, so now for D7, here we are having 1, so we will keep here 1. So 1 by 2 plus, D6 is also 1, so 1 by 4 plus 1 by 8 plus 1 by 16 plus 1 by 32 plus 1 by 64 plus 1 by 128 plus 1 by 256, and this is equal to 2 milliampere multiplied by, here we take, so LCM will be 256, right, and 2 divided by 256 divided by 2 is 128, right, so 128 plus 256 divided by 4 is 64, so 64, in this way here for this term you will get 32, for this term you will get 16, for this term you will get 8, for this 4, for this term 2, for this term 1. So this will be equal to 2 milliampere, and if you add all these of these, then 255 divided by 256, and this is equal to, we calculate this, 255 divided by 256 is equal to this, multiplied by 2 is equal to this. Okay, 1.99. So this is 1.99 milliampere. So this is the maximum current which can be generated from this ADC for this particular configuration. Now here, so this I out is approximately equal to 2 milliampere, which is your I reference, but it is slightly less than I reference. So this is about the maximum current which can be generated from this DAC. Now step size. So there is term for DAC also, step size. Step size. Now the step size for this DAC is the maximum change in output current or output voltage when the digital input value is going from one state to next consecutive state. So this is your step size. Now for example, if our digital input is, can you write D7, D6, D5, D4, D3, D2, D1, D0. Suppose our digital inputs are 0, 0, 0, 0 and 0, 0, 0, 0. This is our digital input 0, 0, H. Now under this condition, what I output we are getting? That is 0. Current will be 0. So this is 0. Now if we change the input from this state to next consecutive state, so next consecutive state is 0, 0, 0, 0, 0, 0, 0, 1. That is 0, 1, H. So at this time, when system is going to next consecutive state, at that time, what is the value of I out? What is the maximum change in I out? Or what is the maximum change in V out? That is called as step size. So here I out is 0 as well as V output is 0. So here if we calculate for this input condition, the value of I out is, you apply this formula, I reference is 2 milliampere. Now D7 is 0, so here you have to keep 0. So all are 0 except D0 bit. D0 bit is 1. So here we will put 1 for D0 bit. So we are having 1 by 256. 1 by 256. You just find out this value. Divided by 256. So it is coming 0.0000781 milliampere, or you can write it in terms of, or just we will write it in this way, 1, 2, 3. We will save the decimal 3 points right side, so it will be 7.8 into 10 raised to the power minus 3 milliampere, and this 10 raised to the power minus 3 milliampere is microampere. So this is 7.8 microampere. So this value, these value. So when system is going from this state to this state, at that time, in the second state, we are having a output of 7.8 microampere. So this is the step size. 7.8 microampere is the step size. Or in terms of V out, we find out the V out. So whatever is the V out is, here we will write V out is I out multiplied by RL, and I out we are having this 7.8 into 10 raised to a minus 3 milliampere multiplied by here. Now this RL, we will select this RL. Suppose we want to get a maximum output. See, here we have connected a maximum, this V reference by 5. So here maximum output we will get here 5 volt, right? This is the V out. So that is the maximum output. So now to get this, actually it is, we have to select the value of one resistor to get this output. So for this output, the value of resistor will be RL is equal to V out divided by I out. So V out is, we require a 5 volt full deflection, divided by I out, we consider it as 2 milliampere. So it is approximately equal to 2 milliampere. So with this way we can calculate it. So it is 2.5 kilo ohm. So this RL is 2.5 K. So that we will write here. So 2.5 into 10 raised to the power 3 ohm. So this will give 7.8 into 2.5. 7.8 into 2.5. So this is giving 19.5 millivolt. So this is giving 19.5 millivolt. So in this case, if we are giving this input combination to this DAC, then output current is 7.8 microampere or 7.8 into 10 raised to the power minus 3 milliampere, and output is 19.5 millivolt. So this is our step size, or we can call this also as our step size in terms of our voltage. Now suppose we want to generate output of, let us assume 2.3 volt. We require this output. we want to generate here 2.3 volt, right? 2.3 volt. Because with now, if we reduce this voltage, then the speed of this DC motor will reduce. Now suppose in some application we want to reduce the speed of DC motor. So we have to, in that application, suppose we want to generate here output of 2.3 volt. So for this, what should be the digital input we shall give so that we can get 2.3 volt output. So if this is our application, then we shall use this formula. Step size multiplied by n number is equal to V out. So in terms of output voltage, if we are talking, then we will take the step size this. So step size is 19.5 millivolt multiplied by n is equal to V out. Required output is 2.3 volt. So we will find the value of n. So this is 2.3 volt divided by 19.5. Now millivolt I will convert in voltage into 10 raised to power minus 3 volt. So for this we will find out the value, what value we are getting. .3 divided by 19.5 is equal to this, multiply by 1000, 1000, okay, 117.9. So this is giving me a value 117.9. So I convert it in a round figure. So I will get here 118 in decimal. So to generate an output of 2.3 volt, we have to apply a binary 8-bit binary value of which is equivalent to 118 decimal. So we will calculate this value. What in binary? What is the binary value for 118 decimal? So for this, we will just write the weight of these values. So this is the weight of D7th bit is 128, D6 bit is 64, D5 is 32, D4 is 16, then D3 is 8, 4, 2, 1, and we require 118. So 0, 1, 1, 1, 1. How much it is? 64 plus 32, 96 plus 16, 112. 112. We require 118. 112. Make it 0. Plus 4. 116. Plus 2. 118. And this is 0. So this is the value. This is in hexadecimal. If we write, this is binary value. In hexadecimal, it is 7 for this, and this is 76H. Now to generate a 2.3 volt, we have to send 76H to these digital lines, then we can get 2.3 volt. So in this way you can calculate the what is the required digital value for particular output voltage. Now in next lecture we will see few applications of this DAC. How we will write the program so that we can generate some triangular wave or sawtooth wave. So those programs we will write in next class.